where we had the opportunity to create our own physics adventure. In this lab, I threw a tennis ball in the air and used Tracker to analyze the video. I then created a computer model that mimicked the motion of the ball and calculated the energy of the ball when it was thrown. I then used those values to calculate how many times I needed to throw the ball to burn off the calories of my favorite food, Papa John's cheese pizza. Physics principles used in this lab. Newton's second law was used to update the velocity of the ball. This law states that the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. For calculating the net force, I use the force of gravity and air resistance. Gravity is the attraction between any two objects with mass, and it is equal to negative mass times the gravitational constant g. And air resistance opposes the motion of the object and is equal to negative b, which is a proportionality constant, times the velocity squared. I then use the energy principle, which states the total energy of the system remains constant unless work is done by an outside force, or the change in energy is equal to work done on the system. Some of the equations associated with energy that I used for this project is kinetic energy and potential energy due to gravity. I then can convert the energy of the ball to calories by calculating the total energy of the ball in joules and then using the conversion factor of 1 calorie in food is equal to 4,200 joules. Here's the video of the ball being analyzed in Tracker. In this video, I analyzed the motion of the ball along the y-axis. I used my height as a reference measurement and calculated the velocity of the ball released to be equal to 3.6 meters per second in the y direction. I then created a code that matches the motion of the ball. I started by setting some initial conditions in lines 35 through 54 that are used in future calculations. I then created a while loop in line 62. I then calculated the weight force or force due to gravity by using the formula that I talked about earlier, where the mass of the ball times gravity times the unit vector j hat. I then used the drag force formula that I used earlier, where negative b times the ball velocity squared times the unit vector j hat. I then added the weight force and drag force to equal net force. I then used Newton's second law to update the ball's velocity and position in lines 73 and 75, and in line 78 I updated the time. I then compared the computer model to the observed position. The observed position in red is different from the modeled position, but as you can see, the modeled position that includes drag in blue is much better prediction of the motion, so drag is important to this model. So how much energy does the ball have? For this analysis, I analyzed from when the ball was at rest to when the ball was released from my hand at 3.96 meters per second. The change in height during this time interval was 0.276 meters. We started with the energy principle and expanded this equation, where kinetic energy is equal to the work due to gravity plus the work times the hand. I then isolated the work of the hand and filled in our known equations to find that the work done by the hand is 0.612 joules, and that one toss of the ball is equal to 0.612 joules. So how many times do I throw the ball? One slice of pizza is 304 calories. Multiplying this by our conversion factor, we get that we need 1,276,800 joules. We know that the total energy of the ball was 0.612 joules in one throw. Dividing this by the energy to burn off the slice of pizza, we find that I need to throw the ball over 2 million times. Assuming it takes 0.833 seconds to throw the ball and catch the ball, it would take me about over 41,000 hours to burn off the piece of pizza. So how much would an object have to weigh to burn off the pizza in one throw? We can use our equation before and set the work of the hand equal to the number of joules we want to use. We can now expand the equation and isolate for the mass of the object and plug in the values to find that I need an object that weighs 92,265 kilograms. This is slightly less than the mass of a space shuttle. In conclusion, I need a better form of exercise, and it is surprising how little joules that throwing a ball expends. Thank you for watching.